What's up everyone, Patrick here, welcome back. Moving on to the next question dealing with circles. So we are told that the points A, 17 and 1, B, -3 and 5, and then C, 9 and 9, lie on a circle centered at 6 and -2. And two parts to this scenario. So part A, we have to find the equations of the right bisectors of the chords AB, BC, and AC. And then in part B, we have to verify that all three bisectors, right bisectors, pass through the center of the circle. So if you remember, the right bisector of a chord always passes through the center of a circle. We've gone through that in a previous video, so just as a quick review. So to show this as a quick review, as a diagram, so if we have a circle, so let's say its center is like right here, approximately. If we draw any chord, remember what is a chord? Well, if we take any 2 points on the circle, so let's say right there, so we have this chord over here. If we draw the right bisector of this chord, remember what is a right bisector? It's basically a line that's going through the midpoint of the line segment you're looking at, and it's perpendicular to that line segment, right? So here we have the chord, and then here we have the right bisector of the chord. That right bisector of any chord of a circle is always going to go through the center. So if we draw another chord, let's say like over here, like that, and then we draw the right bisector of that chord, right? It's going to go through the center as well. All right, so the right bisector of any chord, they're always going to go through the center of the circle, or they're going to intersect at the center of the circle. We're going to go through a question in a future video where we're only going to be given points on a circle. We're not going to be told what the center is, and then we have to find the equation of it. And this is what we're going to be using, where we've got to find multiple chords, find multiple right bisectors of those chords, and see where those right bisectors are going to intersect. So to draw another diagram here for this scenario, so we got a circle. We're told it has a center at 6 and -2, and then we're given 3 points on the circle. So let's say A is like over here. This is not necessarily how it's going to look on a Cartesian plane, but just to have a rough diagram to follow. So we've got B, which is -3 and 5, and then let's say C. Let's space it out a little bit. Let me think here. Yeah, let's put C over here. Doesn't matter where you put it, I'm just trying to make sure that the chords are all going to be spaced out okay. So C, 9, and 9 like that. Okay, so what we're going to do is we're going to find the right bisectors of the chord AB, right, and then BC, and then AC. We're going to find those 3 right bisectors, then we have to confirm or verify that those 3 right bisectors are going through the center. So let's first find the right bisector of this chord, AB, right here. So the right bisector of AB. So how do we find that? Well, what we first want to do is find the midpoint of AB, right? Because that's the point that the right bisector is going to be going through. So let's first do that. So we'll find the midpoint of AB. Now the midpoint formula, x1 plus x2 divided by 2, y1 plus y2 divided by 2. So what we would do is we would add up the x values of the A and the B. So we'll have 17 plus -3 divided by 2. Then we'll add up the y values of the A and the B, and then divide that by 2. So 17 plus -3 is like 17 minus 3, which gives us 14. That's going to be over 2, 6 over 2. So we'd end up with 7 and 3, like that. So this midpoint here has a coordinate of 7 and 3. Now what we want to do is we want to find the slope of AB, because after we have the slope of AB, we will get the negative reciprocal of that to get the perpendicular slope of the right bisector. And then once we have that slope of the right bisector, we also have a point, then we could find the equation. So let's find the slope of AB, which is going to be y2 minus y1 over x2 minus x1. So let's actually label this. We'll have x1, y1, x2, y2, like that. So we would have y2, which is 1, minus y1, which is 5. Then we'll have x2, which is 17, minus negative 3. This would be negative 4. 17 minus negative 3 is like 17 plus 3, which gives us 20. This would simplify to negative 1 over 5. Like that. So that's the slope here of AB, but we don't want that slope, we want the perpendicular slope. So the perpendicular slope, or the slope of the right bisector, is going to be the negative reciprocal of this. So we flip it, which would be 5 over 1, change the negative to a positive. Positive 5 over 1 is just positive 5. Okay, and now we have enough information to find the equation of a line. We have the slope of this line, which is positive 5, and then we have the point that it's going through, 7 and 3. And so to find the equation at this point, we just do y equals 5x plus b, and then we could solve for this b value, plug in the point, so we'll have 3 for y, plug in 7 for x, so we'll have 3 equals 35 plus b, bring the 35 over. The b value is negative 32. Okay, so the right bisector of AB, this line over here, it has an equation y equals 5x minus 32. Okay, and even though we're going to be verifying in part B that the right bisectors are going through the center, if you want to, this is, for example, a question on a test, if you want to check your work while you're doing the question, what you could do is when you get this equation, you quickly plug in the x value of 6 here, and you should get a y value of negative 2, if that line is indeed going to go through this point 6 and negative 2. And notice that if we plug in 6 here, 5 times 6 is 30, minus 32 is negative 2. Okay, so we could be pretty confident at this point that that is the correct equation. It doesn't always guarantee it. It might just be coincidence. You might get a wrong right bisector. It might be a coincidence that it still goes through that point, but the chances of that happening are pretty slim. Okay, so we can be pretty confident that this is correct over here. So now what we can do, let's find the right bisector. Let's do BC. Okay, so what we would do, let me erase this over here. Now what we're going to do is we're going to find the right bisector of this chord over here. So again, we got to find the midpoint, find the perpendicular slope, and then again it's going to be going through that center right there. Any chord that you draw, it's going to go through that center. So let's first find the midpoint of BC. What do? Add up the x values, divide by 2, then add up the y values, divided by 2. So this would be 9 plus negative 3 is like 9 minus 3, which would give us 6. 9 plus 5 is 14 over 2. So this would be 3 and 7, like that. Okay, so this midpoint here has a coordinate 3 and 7. So now let's find the slope of BC, y2 minus y1 over x2 minus x1. This one is a little, for the slope I recommend, oh no, we already have B labeled as x1, y1, so I'm going to label C as x2, y2. Okay, for the slope I recommend labeling it just because with the slope it really matters that things are in order, right? The x2 has to be at the bottom of y2, the x1 has to be at the bottom of y1. So y2 is 9 minus 5. So y2 is 9, y1 is 5. Yeah, and then x2 is 9, and then x1 is negative 3, like that. So this would end up being what, 4 over 12, right? 9 plus 3 is 12, so this would simplify to 1 over 3. So that's the slope of BC over here, but we want the negative reciprocal slope, the perpendicular slope, so we would flip this, change the sign, so the perpendicular slope would be negative 3. Okay, so this here, this right bisector has a slope of negative 3. And then we would find the equation of the line with a slope of negative 3 going through the point 3 and 7. So we would have y equals negative 3x plus b. Plug in 7 for y, plug in 3 for x. Bring the negative 9 over, 7 plus 9 would give us 16. Okay, so the right bisector BC, of the chord BC, has an equation y equals negative 3x plus 16. And again, if you want to do a quick check, plug in the center, let's plug in the x value. Negative 3 times 6 is negative 18, plus 16 does indeed give us a y value of negative 2. So we could be pretty confident that this is the correct answer, right? So this is the equation of this line over here, right? And then finally, let's erase this so there's not too much confusion going on. I'm going to keep the chords though. So now what we got to do is we got to find the right bisector of the chord AC. Sorry, I erased the point. This point was around here. So now we got to find the right bisector of this chord AC. So we got to find the midpoint, and then it's going to be the perpendicular line going through that midpoint. And notice that that line as well should go through that center right there, right? So we're finding this right bisector now of AC. So same steps. Let's first start with the midpoint of AC. So it's going to be the x values added up, so 9 plus 17 divided by 2, and then we'll have 9 plus 1 divided by 2. The y values added up, divided by 2. So this would end up giving us 26 over 2, 10 over 2, which would be 13 and 5. This point over here, it has a coordinate 13 and 5 like that. Now let's find the slope of the chord, of this chord AC over here, and then we'll get the perpendicular slope. So the slope of AC equals y2 minus y1 over x2 minus x1. So got x2, y2 over here. I'll label this as x1, y1. So we'd have y2, which is 1, minus y1, which is 9, over x2, which is 17, minus x1, which is 9. So this would be negative 8. Over 17 minus 9 gives us positive 8. This would be negative 1. What's the negative reciprocal of negative 1? Well, negative 1 is like over 1. We flip that, change the sign, and be positive 1 over 1, which is just 1. Okay, so this chord had a slope of negative 1, so that means the right bisector has a slope of positive 1. Now, on the diagram, it doesn't look like that because remember, these points are not to scale, right? If you draw this on a Cartesian plane, these points will all be located differently. Like notice how the right bisector in the diagram has a negative slope, but in reality, it actually has a positive slope. If you were to draw these points, I just drew a rough diagram. So we got the slope of the right bisector, which is 1, and then we have a point, 13 and 5, that it's going through. So let's write that out. We got the slope of 1, we got a point it's going through, 13 and 5, so we'd have y equals 1x, which is just x plus b. Then we could plug in 5 for y, and then 13 for x, so b would be 5 minus 13, which would give us -8, like that. So the right bisector of AC, of the chord AC, would have an equation y equals +1, so x minus 8, like that. And again, you can do a quick check. It should be going through the center of the circle. If we plug in 6 for x, 6 minus 8 does indeed give us -2. Okay, so those are the equations right there. And if we redraw all those right bisectors that we erased, notice that all of them are intersecting at that center of the circle, right? We got a right bisector, right bisector, right bisector, like that. Okay, so they're always going to be going through the center. The right bisector of any chord is always going to be going through the center of the circle. Okay, and then to verify, it's basically what we did when we were doing the check. So all you do is you plug in the x value of the center into each of these lines and make sure you get the corresponding y value of the center. So notice with this, verified, y equals -3x plus 16, plug in 6 for x, -18 plus 16. We also get a y value of -2, verified, y equals x minus 8, plug in 6 for x. We also get a y value of -2, so that ends up being verified as well. Right, so if you get this over here, you're done with part B. You're verifying that it goes through the center. All right, so we've gone through that rule or that property before of where the right bisector of any chord is always going through the center of a circle, but now we did it with a circle that's not centered at an origin but at a different point, and in this particular case the point was 6 and -2.